So let's look at the results of an actual experiment where people have taken electrons and fired them through two slits and seen what happens on the screen. So what you're seeing there are individual blobs of white light when an electron hits the screen. And when a single electron hits the screen, we see a flash of light, and so we can tell that actually electrons are particles. So unlike waves, they're particles. And that's what we'd expect to see if we were sending a very small number of particles through. We wouldn't see a big fuzzy blob. What we'd see is individual strikes. If it had been a wave, then we would have seen a weak interference pattern. So it would have been those bright and dark interference fringes across our entire screen, but very, very weak. And instead we're seeing these blobs. So, all right, they're particles. But you'll notice that as the speed of the movie increases and we see more and more of these blobs, then something rather strange is happening. We're seeing that those blobs are more likely to appear, the electrons are more likely to strike where the bright fringes of the interference pattern would have been if it had been a wave. And they're much less likely to strike where the dark fringes of the interference pattern would have been if they're a wave. And so what we've discovered is that both of these theories, the particle theory and the wave theory, are wrong. If the particle theory had been right, then we would have got these blobs, all right, but they would have, on average, not made some lovely interference pattern. They would have just ended up making this big smooshed out blob. And if the wave theory had been exactly right, we wouldn't have expected to see blobs at all. We'd have expected to see a weaker and weaker version of that interference pattern. But instead, we need a hybrid theory that can explain both the blobs appearing and the eventual interference pattern. And that hybrid theory is what we now call quantum mechanics.